definitely be chilled. I'll stop for that. But yeah, so really I'm going to kind of cover my work on core collapse supernovae. That's what I study specifically, and what my most recent work was on. It was kind of turbulence and turbulent dynamics in core collapse supernovae. So I'll mostly cover that. I do a little MHD stuff too, so you're welcome to ask me questions about that, but mostly this will be about turbulence and stuff like that. This is kind of a fun little picture that comes out of my research sometimes. One of the big benefits of doing like 3D MHD stuff is you get like really pretty pictures. Even if I made up the data, that's fine, you know. It's really nice to look at. Made up theory, whatever, you know, same thing. So I'm gonna go ahead and make my computer work. There we go. So just a quick like overview, what core collapse supernova are, how they work, right? So they're generally core collapse supernovae happen as the end of lives of massive stars. So when they're in excess of like 8 to 10 solar masses, that's when you start to get core collapse actually happening. And there's like huge events, right? Their luminosity will outshine like host galaxies. They spit out like 10 to the 53 erg of energy. If you're not familiar with erg, that's something that the SI police lets us use as physicists sometimes. So we get to use our CGS units once in a while. They have all kinds of crazy physics. It's like really cool places to understand like really extreme scenarios, right? So you have like these powerful magnetic fields. You can get like, so I saw some interesting papers about like quark deconfinement can potentially happen in like these like protoneutron stars at the core. Gravitational wave signals, that's a space of study right now that people are really interested with this. Really high densities, really odd neutrino physics, and some beyond standard model neutrino physics as well. So you can get some really interesting constraints on some neutrino properties. That's kind of a side project I worked on too. You can bother me about that as well. And all kinds of wacky things happen. And I'm going to kind of just go run through the overview of like what happens in a core collapse supernova, because there's a specific piece of this that I need to talk about, or just a particular piece of like what goes on. So, you know, I know there's a lot of solar stellar people here, right? So a lot of fusion goes on at the core collapse supernovae, or generally in stars, right? That's how you feel these things. And so core collapse supernovae kind of initiate when you fuse down to iron, right? So iron has a negative binding energy per, or has a negative slope on the binding energy per nucleon graph. So it's an endothermic, you know, nuclear reaction. So it costs more energy to produce than you get out. So it doesn't fuse beyond. So stars will fuse. And if you exceed 8 to 10 solar masses, you can fuse your carbon and oxygen layers down to silicon and iron, and you build up this iron core. And this iron core will accumulate and eventually build up to cross the Chandrasekhar mass, so 1.4 solar masses. Once you cross that threshold, the electron degeneracy pressure from the iron nuclei that are sitting at the core can't hold up against gravity anymore. And so they sort of like give in, right? They collapse. And this is the onset of the core collapse for a core collapse supernova. So really rapidly, basically these iron nuclei just like get shoved into each other. Electrons get shoved into protons. You get a kind of a ball of like heavy neutron, a heavy ball of neutrons that just sort of like collapses really quickly. And this like space that's now empty gets collapsed in from above with all the material that's sitting on top. And so this happens. The material collapses down to the core. It reaches some sort of like we can call it like some NSE, some nucleostatistical equilibrium situation where it doesn't want to collapse any further, right? The equation of state stiffens really heavily. And so the iron core, that's now mostly just neutrons, right? This like sort of proto-neutron star collapses, crosses past this point of equilibrium, and then bounces back out kind of to an equilibrium state. And this core bounce is where this like initial shock wave comes that will ultimately like drive the explosion of a core collapse supernova. So this core collapses, bounces back to equilibrium, and sends this like outward moving shock front outward through the stellar material. So you have this like, you still have some iron core going on, you have silicon, and you have all kinds of other nuclear material. It's just sitting above that's now going to get thrown out. And so this is kind of the piece where I do a lot of my research, this phase of the star, because the shock and ultimately stagnates. So as the shock is moving out, it's like losing energy like crazy. There's a bunch of nuclei falling in. It's like photodissociating these nuclei. And so as it like photodissociates these nuclei into just like free protons and neutrons, you're expending energy. Eventually this shock, at least in our models, right, show that this energy gets expended until about 100 to 200 kilometer range and stagnates right there. And so this is like the shock stagnates and now is no longer supported by that initial energy. The only thing that's actually keeping the shock up is mass accretion through the shock. So as mass gets accreted onto the core, you know, more material just increases pressure at the core and, you know, stabilizes the shock. And so for a little bit of time, we're talking on scales of like milliseconds here, you know, maybe like 60 to 100 milliseconds, you have a standing accretion shock. So the shock kind of just sits stably here. And this is where the supernova can or cannot become a supernova, ultimately, the pre-supernova situation, depending on what happens here to revive the shock. So the current theory and the current sort of working system here is this delayed neutrino heating mechanism. So as these, as this nuclear processes are going on in the core, as protons and electrons are getting shoved together to produce neutrons, you need to preserve lepton number. So electron neutrinos and electron antineutrinos are getting like dumped out in crazy volumes, right? You get like 10 to the 53 neutrinos getting emitted in one of these events. These neutrinos, while they generally have like very small interaction cross sections, or very like weak chances of interacting, are at densities of like 10 to the 14 grams per centimeter for the surrounding matter, and are also just high in flux and energy. So you have a high chance of actual neutrino interaction. So these neutrinos are generally providing enough heat and energy to potentially revive this shock. This is kind of the accepted theory of how these core collapse supernovae revive their shock. But the means by which this actually happens is an area of study, right? You kind of got to understand how this energy reaches from this core, right, from deep in this core out to actually where the shock is 200 kilometers away, right, 150, 200 kilometers away. And so that relies on convection, that relies on turbulence, that relies on like a lot of like fluid mechanics, and also just in general how able these neutrinos are to deliver this energy, just like cross sections and things like that. So that's kind of the key point. If this energy can't be, can't overcome the external ram pressure of the things falling inward, then it will collapse into a black hole. Otherwise, if you can get enough energy to sort of revive the shock and move it back outward, then you achieve a supernova. So in this case, the neutrino heating was sufficient in this image here, and the shock is able to travel back out, and you ultimately will have shock breakout. The shock will like kind of move outwards, blow up the star, and you'll be left behind with a neutron star remnant. Yeah, hit me. Yeah.
Just look for it. I think the shock stalls.
Yeah.
By that, do you mean that it becomes stationary, or do you mean that it ceases to become a shock? And if you mean it's stationary, is there some physical reason why it should sort of stop?
Yeah, so it is stationary. I mean, it is there are some interesting, there's something called a standing accretion shock instability where it does move a little bit where it is, but it generally stays at a fixed radius. The reason is because the pressures match basically. So there's material accreting inward, and that material that's accreting inward onto the core through the shock front, building up. And so that's providing a pressure here, right? This like sort of a buildup of just mass at the core that's providing an internal pressure that pushes it out. Meanwhile, it's fighting the external pressure of material just like sitting on top in gravity. Now, this is like a very brief period. This is like 60 milliseconds to 100 milliseconds, but it does have some level of stability where it just sort of sits there and stands. So yeah, it does stay stable for a little bit of time. And that's why we're really interested in it, because this is like a really critical moment where it can kind of decide which way it goes. Is that clear? All good? Yeah.
So the standing accretion shock instability can really make the whole system unstable, or it will just
it can actually blow up. Yeah, so the standing accretion shock instability, I don't know what you know about it. It's called SASE, really was what we call it, which is kind of fun. It's when you have some rotation and you have some high level rotation of the star, and you can have you can imagine some material being sort of off axis here. And so if you have a shock sitting somewhere right here, and some material like flowing in, but it's off center, right? Rather than just flowing in radially, maybe it flows in like a little bit off due to rotation or asymmetries or whatever. You kind of get this instability where it starts to like, the shock starts to wobble, and you have these like high like modes that show up. But you can actually like promote explosion from that. So these are actually things that can like tear apart the shock and like result in an explosion. And that's actually a really good segue. And kind of my next point here is that there's a whole bunch of means of like how these things can explode. So I mentioned that neutrino heating is kind of the primary accepted mechanism, right? But there is like other things. We don't have to worry too much about what this plot actually shows. I just kind of like nabbed this from a paper to show that there's a lot of, here's the shock radius over time of some kind of like supernova simulations. And this is the heating rate over here from neutrinos. And you can see generally the correlation between high neutrino heating rate and then shocks kind of expanding when the neutrino heating rate crosses a certain threshold or reaches a certain level. But I'm going to jump one slide ahead. I'll come back to this. Rotation also plays a huge part in that too, right? So this SASE, this standing accretion shock instability, can also drive this explosion by having just a lot of rotational energy in there too, to sort of like throw it out. Really neat work I've seen recently by this guy, Adam Burrows, who did something on like, you can actually get, if you have a strong enough SASE, a strong enough standing accretion shock instability, you can actually get a remnant black hole and still blow up the star, which is kind of a interesting scenario. He's done a couple models on that, just because you can like still collapse into a black hole, but you have enough material that's sort of like offset and like off axis that it still throws things out in like shockwave type manner. That makes sense. So, okay, bit of an aside there, but yeah, so that's kind of all the details for that. And then what we care about, and kind of what I care about when I'm like really looking into, is like how we can move this neutrino energy, this neutrino heating energy into, so that happens down deep in the core. That happens kind of over here. right, where this proto-neutron star is, the standing accretion shock is somewhere sitting at somewhere up here. And so we have to sort of kind of transport that heat down from the core up to the top. Generally, you know, you think buoyancy can do a lot of this, right? Just general heating, right? You have like less dense, hotter material will move it up. But there's a lot of inhibitors to that, right? I mean, you can have convection cycles, you can have turbulence, you can have all kinds of dynamics in 3D that just like aren't modeled in 1D. For context here, most supernova simulations are done in 1D. Well, most prior to like, I don't know, maybe 10 years ago, 20 years ago or so, because 3D is kind of expensive to run computationally. As I'm sure some of you may know, I hear a little bit about Caroline's research is 3D and stuff. But all that to say is there's a lot more complexity that goes onto it in 3D that we have to account for, right? Turbulence and magnetic fields and all these sorts of things. So I jumped around a little bit. Let me just kind of move on or keep going with my point here. Yeah.
What parameters that you're varying? Is it the mass, the star, and the rotational rate in the previous slide?
In this one? Yeah, this is from a Couch and Ott paper. So I can run you through it. So in general, in supernova lingo, so the letter that goes in front of your model is your metallicity that you start with. So solar metallicity, then this is your mass, your progenitor mass, and solar masses. So 12, 15, 20, 70, and 40. And then these are different choices for the equation of states. So basically just sort of how you handle the pressure and density relationships and YE at the core. And so these are from a paper I stole, or sorry, this is a figure I stole from the paper from Sean Couch. And it's basically just kind of highlighting that when, I think these are 1D models as well. So in 1D even, it's clear that when you add neutrino heating, just highlights the fact that your shock radius is sort of like going out. It's like kind of the primary driver for the energy source here, because you can see something like neutrino energies get crazy, and they're the biggest energy source in these simulations. Also notably, and worthwhile mentioning for this talk, in 1D, supernova don't explode, even with neutrinos included. So you have to actually add like some artificial mechanisms to blow them up in 1D, or you can model them in 3D and they blow up on their own. So that tells us a lot about how important this like 3D mechanisms are, right? The magnetic field and the turbulence. So to get to my work, I guess, I've just kind of run through that magnetorotational stuff is important, but then turbulence is also important. So, you know, Couch coming through again with another reference here, but this is a 2D simulation that they did, and they could sort of like do their own version of like turbulence and convection and things like that in 2D. And you can kind of see on the right-hand side here, the top plot is what matters the most, which is the shock radius of this thing, which is just generally tracking where the shock goes. And when you see the shock move outward, you know the star has kind of exploded. And you can see in their different models, when they include convection and they include this like turbulent features, they have actually like a much more rapid explosion. You can see that green line sort of like blows out there a lot more quickly. And that's tracking their 2D model that they've included these turbulence factors in. But at the same time, for these models, they needed to have a pretty high resolution because you need to actually capture these like small scale features, right? This turbulence is like on scale like 10, 20 kilometers in size.
So I don't know what I can play in the sun.
Yeah.
What does it look like in these things?
Oh, well, let's see if I have a handy video. Well, I mean, honestly, I can just show you, I could point you to my opening slide here because you can see it in this animation. I mean, like what it like literally looks like is just kind of like this, but it's very similar sort of stuff to the sun, right? So there's a lot more complexity in terms of like the heating and stuff like that because it's non-constant, right? These are dynamic, these are non-steady state systems as compared to like solar stuff. It's a bit more steady state, right? But generally you get these like strong downflows, and then you'll often get some kind of asymmetry where there's like one direction that like loses this fight somehow, and you get this like breakout or like push outward. And understanding that is something that's not like well studied because there's not been a lot of like 3D MHD studies on these things, just because it's hard to do, and it's kind of novel that we have this like ability to do these studies at this point. So this is kind of like what convection may look like in this sort of system. So running through
So what is the mechanism which is driving the turbulence here? Is that convection or Sassi enters into the nonlinear state and is driving?
So what is you said what's driving the turbulence?
Yeah.
Yeah, so I mean that's honestly a great question. I mean, it's kind of the point of what we're getting at here. It's like you know, there's a lot of different asymmetries that go on. There's a lot of like heating that you can sort of like imagine is gonna like cause little eddies or cause some big convective cycles or things like that. But there's also just a lot of strange properties that go on in 3D that generally show up as turbulence. But it's also just sort of like any kind of turbulence you'd expect in any kind of flow, right? You're not going to get like perfectly laminar flow from the core up to the shock in 3D because there's going to be some kind of like divergence somewhere, right? The velocity is going to be moved offward for one reason or another. Maybe some material is falling in and pushes it this way, or some magnetic field could, generally either promote or misalign, or sorry, promote or hinder the potential for turbulence. So there's kind of a lot of factors that could go into it, and that's kind of like what we want to look at and what we want to understand as well. There's general asymmetries that come out of this, right? Because in theory, right, if this is a perfectly symmetrical simulation, which it is when we start, because we start from a 1D model and we just like rotate it into 3D, you would expect like a perfect just 3D, like perfectly symmetric everything, right? There's no reason for these instabilities, but there's numerical noise and things like that. And in real life, these things are asymmetric, right? So we kind of just like leverage the fact that there's like small numerical noise that introduces asymmetries to then model these real asymmetries in real life, right? Generally, in a perfect world, we would have asymmetric 3D progenitor models, like stellar models that people have evolved just to collapse that have already these like asymmetries built into them. But those are also computationally expensive to run. And for whatever we don't know about core collapse supernovae, we know even less about stellar evolution beyond like, I don't know, what we can measure about our sun, right? So a lot of these things are kind of difficult to get accurately. So we kind of just start with a 1D model because, in this onion shell picture that I've drawn here, that you see kind of here, maybe I had as the first piece of this slide, is generally a pretty good approximation, but of course there's going to be some mixing and things like that we have to consider. So long-winded answer to say there's going to be general asymmetries that kind of causes turbulence, and we're just kind of taking for granted the fact that we know that there's probably turbulence. We know it's necessary for these explosions because we can see that by running a 3D and seeing how 3D models blow up when 1Ds don't, right? So there are 3D processes that need to happen. Okay, so ultimately, question here, right? How does turbulence below the shock alter these energies and alter where energy goes to in core collapse supernova? That's kind of what we want to understand. That's what I seek to label here. And I use a tool called Elephant, which is one of those fun acronyms where they make a word out of it and then figure out what it stands for later. So it's the elegant and efficient, some other stuff, who knows, right? They just add the words elegant and efficient, and then it's like some kind of hydrodynamics and neutrino transport code. But the kind of novel piece about this code that I work with is it does two things. One, it utilizes Cartesian coordinates, so it has like a fixed grid everywhere. So that's kind of a nice benefit because you can get high resolution in regions you might not otherwise with adaptive grids. And two, it's really easy to parallelize. That's kind of the strength of it, is it's like super parallelizable. You can just break it into like cubic chunks and then like send them out to all these like nodes to work on. So that's like super cool. It's like super awesome. My only drawback, and this is my personal experience, is that supernova generally more spherical than I would say cubic, right? So it's kind of hard to fit like a cubic grid and do a lot of analysis on a spherical object, but we make it work, right? And with that note, it's going to kind of motivate some of the things that I'm going to be showing you guys in a minute here. Right, so kind of like I already talked about a bunch. There's like three main things that I kind of care about in these like 3D simulations, right? Yeah.
You said adaptive mesh is not as high resolution as the Cartesian. That doesn't make sense.
Oh, well, an adaptive mesh is more high resolution in certain regions, but at least with a fixed grid, like this 1 kilometer fixed grid everywhere, we can get the same resolution everywhere, and we can get a higher resolution in regions where you might not look directly with an adaptive grid, right? So instead of having like, I guess you could just choose to make your adaptive grid however you like, right? You could like have a really high resolution at the proto-neutron star and then really low resolution elsewhere. Yeah, okay, that's fair. You're so right. There's benefits and negatives to each, and I also like the adaptive grid, except right now I'm fighting with a code that has an adaptive grid, and it's giving me a headache trying to understand how it decides where to put the grid. Probably because people smarter than me wrote the code, mostly it. But yeah, so I guess more my point was just that there are regions where you can get more resolution than you wouldn't normally expect. Because I think especially with adaptive grids, they're usually on spherical kind of codes. And so it's usually kind of radial dependent. So you'll usually get like high resolution either at the shock front where the most highest dynamics are, where the most interesting dynamics are, or at the core, because you'll kind of like be like, I want to see what's going on in the core. And then I like make my grid more coarse as I go outward. And you kind of lose a lot of the resolution that happens underneath the shock. So for this code and in core collapse supernova world, 1 kilometer length scale resolution in the gain region, or the region that I'm going to be talking about, is like really high comparatively, because most people kind of do this adaptive grid where it's high resolution here at the shock front and then here and then at the core. So that's kind of, I guess, high resolution for what we studied too. Right, so these physics, so I kind of highlight this a bunch, but like these are the kind of three key physics that I kind of focus on with this MHD modeling, is the magnetic fields, the heating, and the turbulence. And they're all like nonlinear, all tied to each other, so that makes it all confusing. But in this talk, right, and kind of as we're going, I've already kind of said the word turbulence like 10 million times. We're going to be looking at turbulence. So for my work, this is actually models I've run now, so not anybody else's stuff. This is all on control data. So like control being I turned off the magnetic field, I turned off the rotation. And I really just looked at 4 models and kind of compared how their turbulence behaves in these in the evolution. So kind of like I hinted, when you see the letter S, that means solar metallicity. So I work with 4 solar metallicity models of 4 different masses, 15, 20, 23, and 27 solar masses. And then you can kind of see here, there's a bit of a faded thing, but in 3D compared to 1D models, you can very clearly label where the shock radius is because it's just in a fixed radial zone because you're kind of averaging over all the angular stuff. But here it's not so clear. So you can see the shaded regions. That represents the maximum, minimum, and average shock radii over time. You can see kind of different behaviors of each of these models just by varying the progenitor mass. And you can even see for this 23, it did not explode. It actually very interestingly developed a SASE. We just didn't run it far enough to see if it would explode beyond a SASE because these cost about 1 million CPU hours per run, and we ran out of CPU hours. So it'd be interesting to study how that S23 goes on.
The difference on these 4 models are only the mass of the
Yeah, that's all that's different between these 4.
But we see that only the intermediate mass, 23 solar mass, the shock radius is not exploding rather.
Yeah. Yeah, but it's not just directly related to mass, right? Because then if the S27 does explode, so even heavier stars do explode. And that also ties into abundances. So generally when people build these progenitors, right, they build these like 1D models that we can start these simulations on. When you run it and you have different like initial conditions and a different like initial solar masses, you can get different abundances of material, which then kind of drive these explosions or not, right? Or hinder, right? I mean, if you don't have enough nuclear burning to provide energy to get you enough neutrinos or whatever it might be, right? Whatever like course of action you have to do to get enough energy, it may not be there in the S23. Famously, the 23 solar mass progenitor is actually really hard to explode. People have a hard time getting that one to blow up for many reasons. I mean, I couldn't confidently tell you why. So for this study, we actually did not talk so much about the 23 solar mass one in terms of turbulence because there wasn't on an interesting region to really study. You can see the shock moves out and it kind of just tracks, and it hasn't collapsed into a black hole yet, but it's kind of sat stagnant for a little bit. So for the turbulence study, at least we didn't look too much into it, but I am interested in why that actually doesn't blow up compared to the other models. Actually, I'll give you one last piece of this. I know I'm giving a long-winded answer here, but also there's a parameter called compactness that you generally measure for a progenitor just before you blow up a supernova. And it's generally it's kind of like density. You just measure, what the mass is at some, so you pick a mass, let's say like 2 solar masses, right? And you find at what radius do you achieve 2 solar masses? And you take the ratio of those numbers, and that is your compactness. And it's this parameter that supernova physicists generally use to determine the explodability of a model. So if I had to guess, the S23 probably just has a really high compactness factor, which makes it hard to blow up compared to the other ones. It's kind of like, it's a bit reductivist to sort of say that there's one number that you can look at to say if a supernova explodes, but it has shown a pretty good trend of understanding. So I think that probably has a extra high compactness, and it's probably pretty difficult to blow that up. So one definition here I'm going to dump in is the gain region. So the gain region is the region that we're going to like study and like really focus on for the rest of the talk. And it's really where all this convective and turbulent stuff happens. So I've kind of outlined in black here. So it's all this red stuff above and below these black lines. And it's wholly defined by where the neutrino heating is positive. So basically where the neutrinos are depositing energy and not costing energy to produce. And then the other boundary of that is the shock front. So the upside of it is the shock, and the bottom side of it would be the place at which the neutrino heating it turns from positive to negative. That's all well and good in 1D. You can see there's applications of that in 3D, where like maybe you get some like neutrino cooling, like bubbles, kind of in the gain region. So it's not like a strictly defined region, but I just in my data take anything that's above 0 for neutrino heating. It may have some holes in it, but that's kind of okay. That's kind of the interesting part of the asymmetries here. This analysis, right, this gain region is really what decides the outcome of the supernova shock, and that's why we're focusing on it. That's where all the neutrino heating gets welled up from the base into the shock, and we want to make sure that there's enough heating behind the shock to survive it. So to dig into the nitty gritty of the turbulence, quantifying turbulence is kind of an unclear game, right? I mean, like, how do you say how turbulent or not turbulent something is? The method we kind of took to it was doing a vorticity or entropy search, right? So basically you just take the curl of the velocity, right? You get your vorticity and then square that times density 1/2 because why not? No, because I'm sure there's good reason. And you get the entropy back out. So this kind of gives you a general like scalar value that you can quantify with entropy. You can see here, sorry, that you can correlate with turbulence. You can kind of see over here, there's a bunch of little vortices and you get high entropy in those regions of turbulent. Yeah, turbulent. Entropy is the square of the vorticity, and the vorticity is just the curl of the velocity. So just del cross V magnitude squared. It's kind of it's what we're going to be using as our analog for turbulence. It's our way of saying this is a turbulent region, right? You can see it here. High turbulence, you get a lot of entropy over here. No turbulence, right? General like radial flow. You get a lot of entropy. That's just going to be our scalar comparator here to kind of say, are we doing a good job tracking turbulence or not? Because ultimately, the question I'm trying to answer is how much energy is turbulence adding or taking away from the system? Are we inhibiting or aiding in explosion? And to do that, we have to kind of see where we correlate with where entropy is or where turbulence is. So I'm hoping I'm justifying it to you now that entropy is a good measure of turbulence. And if not, well, you just have to trust me anyway, because I'm up here talking. So entropy is generally a pretty good map for the turbulence. So like I kind of mentioned, it's kind of hard to track what turbulent energy is. There's a bunch of not self-consistent definitions for choice of how we like measure the turbulent energy. I don't know if you guys work with like fluid stuff or Reynolds decompositions, but most of them kind of like leverage this Reynolds decomposition. But the key part and kind of getting to the nitty gritty of like this paper and like really just the math side of things is measuring the deviation. What you need to measure is the deviation of your velocity from your average velocity. So if I want to see how turbulent, perhaps, specifically we're looking at the radial velocity. I want to see how turbulent a fluid is. It's moving in this direction. I want to see how deviant it is from the average radial velocity in that region. Kind of makes sense, right? If we're deviating from radial velocity, then we're probably pretty heavy in the like angular velocity side of things. And that's kind of our way to quantify this turbulent energy. But where the problems come up is the way you choose to average this media, right? The way you choose to take your average is not clear, right? People have chosen a lot of ways in papers, but people kind of just gloss over the fact that you choose an average, we roll with this, and that's just like what it is, right? But like, is that the correct average to be taking? Is that accurately representing what we want to study here? So there's 2 and excitingly now 3 ways to sort of talk about how we average this. The most common one and the most accepted one is like what we're calling in this paper that was in this work, the spherical spatial average. So just a spherical average, right? So we're just kind of assuming that, you know, you take your average radial velocity and you just like do a little spherical shell everywhere, take your average, and that's your average radial velocity. It's really common, probably because a lot of these codes are spherical codes, but also because, well, that's probably the biggest driver of why that's the most common method. But in my opinion, you know, the biggest issue here is that kind of considers regions that are what I call not causally connected, right? I mean, there's some dynamics going on over here, right? These are really complex asymmetric events. And then you're trying to measure over here, you know, what your average radial velocity is. You're not really connecting these two, right? Like I'm pretty far away from what's actually going on over here. So why should this contribute to my average radial velocity over here? So that's kind of, at least my feelings, the kind of gap in that one. There's also the spectral method, which I think is kind of neat and kind of a clever way to like avoid taking averages at all. Which is you just Fourier transform all your data into k-space. Specifically your data of like you look at your like kinetic energy, your spatial map, and you like Fourier transform this. Or sorry, velocity. Either way, they're analogous, right? And then you just like throw away a certain like your wave numbers that correspond to your large scale behavior. So you don't care about your convection, right? You don't care about like, I don't know, just general motion of this like shock. So you just throw away everything above a certain wave number. And then you just transform it back, and whatever's left over in theory is capturing the energy from the small scale behavior. So you should be seeing turbulent energy from turbulent vortices. And then the last method, which is like the sort of new method that I'm proposing here, and that we've kind of like worked out, and is also motivated by the shape of our code a little bit, is like what we call a local spatial average. So in this case, instead of doing like some kind of spherical average where you like reach across the star and try and determine your like average radial velocity, you just look like in your region, you know, maybe like 10, 20 kilometers around you in a cube, maybe, right? Cartesian coordinates. And try and take the average deviation, the deviation from that average. And from our perspective, this is kind of a much more accurate way of measuring how far you're deviating from the radial velocity, right? Yeah.
For your LSA, are you using a Gaussian kernel for the midpoint, or just a step function?
Yeah, just a step function, just straight average. So just like adjacent to me, these all go in my radial average, and I just divide.
Then it is dependent on the size of the cube you are taking, right?
Well, actually, that's a great point. I have a slide about that. So if we've done a lot of studies on like, and that is a whole point, right? That is a parameter that you have to go into this. So it is totally dependent on the size of the cube you take, and that's kind of a bit of an issue. That's also true for the spectral method, right? And actually the spherical method. In all of these methods, in the spectral method, you have to select a wave number to like throw away, right? So I decide a length scale that I care about looking at, and then I throw away everything above that length scale. 40 kilometers, 50 kilometers, 60 kilometers. Who knows, right? How big these turbulent entities can be. We have a general idea, and we can sort of measure this with something called the Taylor microscale, but realistically, you have to sort of like take a stab. The same is true here, right? You can kind of like make an empirical decision about what length scale you want to do for your local cube. And the way you do this, or the way that we chose to do this, was basically just I took a single snapshot of time and I just ran it, calculated the turbulent energy calculated for a bunch of different cube lengths. And I kind of found that there's like a kind of peak that agrees across all our simulations. So this is a bit different data. For context, the color scale here, T10, T12, and control are the magnetic field runs. But really, the point that comes out of here is kind of see a peak right around 20 kilometers. So that's kind of like really where you're capturing the most turbulent energy before you start to like go too far in the other direction, right? If you go too big and you take a cube that's too large, at some point you're just taking the average velocity of the cube, which you kind of expect to be zero, of the whole star, I mean, which you kind of expect to be zero because radial in this way, radial in this way, right? You kind of expect it all to just cancel out with each other. So there are empirical ways to sort of make a selection, but all of these are sort of like touched by having to make a choice somewhere along the line. Same thing with the spherical method. You have to choose what shell width you want to decide on, right? What shell do I care about in terms of how thick I take my spherical shell for my average? So all of these have their limitations, but you have to make a choice at some point. And I think this at least most closely represents kind of what we're trying to study, which is how far we're deviating from local radial velocity. So we have these methods, and really the rest of my slides are just talking about how these things all differ, and right, how we kind of like vary what our measurement from our turbulent kinetic, how we measure our turbulent energy contribution here. Because a big thing, right, like I kind of mentioned, 3D simulations do blow up naturally, whatever, when we run them on their own compared to 1D. So we know that turbulence and convection play a part, but are we stating correctly how much they do play a part? So just to highlight how much different the measurement is. So this is this kind of standard SSA spherical average that I talk about that everybody uses. And this is a spatial map of the turbulent kinetic energy on the right. I know my color bar got cut off. And on the left is the entropy, right? Our sort of check on how turbulent it is. And here it's kind of like washed out, like it's very like light green almost everywhere. And here you see a lot of like fine structure, right? There's a lot of like small behavior. But if I look at our LSA method that we propose, we actually see a much stronger correlation between our turbulent energy. We see high turbulent energy in similar spaces of high entropy, right? So we're actually we think at least more closely tracking what's going on with the turbulence here. It's kind of suggesting this new method is doing a better job of tracking where these little eddies come in and where they're having high turbulence, like where the energy is going into turbulence rather than going into convection or heating. Kind of a bigger picture of this, we can actually see this with all three methods. So on the bottom, I have entropy, and then the top three are the three different methods. Across the board is for three of the runs. So this is the label's kind of cut off by my little zoom thing there, but S15, S20, and S27 for the different runs. So just kind of doing like a particular time snapshot. And we can see that the LSA, right, this local spatial average and the spectral method kind of agree with each other well, but also agree well with the entropy. And I think the spherical method is actually quite deviant from that, right? We see that the method that's been used up to this point is maybe overestimating or maybe just kind of giving too much credence. We see a lot more turbulent energy here than we do in these other methods. Kind of implying that in total, potentially using this method could be overestimating how much turbulence actually plays a part. at least directly. We can kind of see that too if we integrate over time or integrate over space and then kind of plot this over time. So this is just the total turbulent energy. The top 3 panels are the total turbulent energy period. This is as a ratio to the total kinetic energy in the gain region. And these are the 3 methods. So for the first method, right, we can see, especially as a ratio of the kinetic energy, or even just as pure energy, we see a huge spike kind of when the shock expands out. Generally, kind of makes sense with the conclusions that people say that turbulence plays a huge part in this, like, you know, shock revitalization, right? Meanwhile, if we look to the 2 other methods, the LSA and the spectral methods, especially if we look at them as a function of the ratio of the kinetic energy in the gain region, we see that they both, 1, agree with each other, but 2, have a much different story to tell, right? They sort of well underestimate, or I don't know, I want to say underestimate, but they go much lower in terms of how much energy they predict is trapped in the turbulence or caught up in the turbulence. So kind of what this is to suggest is that, for one, this method that we propose is if nothing else, consistent with another method. But 2 here, I think, is kind of shows that we're potentially overstating how much turbulent energy could be playing a part in this. We don't want to say that like outright we are, right? But it matters how you take your average and how you choose to like think about this. There's also one last metric I'm going to throw up on the screen. Don't ask me any hard questions about it. It's called the turbulent adiabatic index. Everyone loves a unitless number that tells you the answer immediately. So we had to make one up. No, we didn't make this up. This is a real thing that exists already. And, you know, on this topic of random stress tensors, I showed earlier a couple slides ago, this like RRR piece is the deviation of the velocity. That's what this delta means, deviation of velocity from its average. So all of these pieces are just measuring how these velocities deviate from their average. So you can think of the RRR piece as the radial velocities deviation from the average radial velocity. And then theta, theta, phi, phi, kind of the same thing. Theta pieces and phi pieces deviations from their average. And because of math, you can stick them together into this way. It makes sense. Sort of think of it as like a ratio of pressure to energy or energy to pressure. And you can get what a turbulent adiabatic index. An adiabatic index that's going to sort of track how turbulent or, you know, how fine structure you're going to get in a region. Generally, what you just want to take out of this is high deviations from radial flow, specifically because we put it in the top numerator here, are going to sort of represent high turbulent kinetic energy. So if you're deviating highly from radial flow, that generally probably means you're turbulent. So you expect high turbulent kinetic energy, but also high turbulent adiabatic index in regions of high turbulence, right? It's kind of like our new entropy, right? Our new way to try this. And you can see done with the 3 methods here. Let me just say okay to that. Let me agree with the terms and conditions. So that we can see the titles here. But really, it's just trying to show that, you know, in the spherical method, just like in the energy, we're kind of like washing out a lot of these things. I know I made this plot a little small and hard to see, but the important piece here is that there's a lot more fine structure that comes out in these turbulent adiabatic indices, which is generally kind of a good thing, right? We want to see that we're tracking these like small pieces here, the small little eddies and things like that. So it's kind of just more of a confirmation of the point that the LSA method is consistent with spectral, but also kind of capturing what we want it to capture, because we're really trying to verify that are we capturing turbulence and are we tracking that? So really, I'm kind of just going to close out here. You know, my 3 key points, I've said it a couple times, right? But just how you measure your turbulence in these situations matters. And turbulence is critical, right? We do need to understand it and know it because it's necessary for the modeling, but really hard to quantify, especially as as you add dimensions, things get more and more complex. And, you know, our current methods are potentially overstating how much we need to focus on it or how much this is contributing. So we need to make sure we're being precise in what we talk about. And then what this leads into, and kind of a bit of a teaser for the next release of my, I don't know, whatever, next archive release, is that, once you stick magnetic fields in this situation, now that we have a means of tracking this thing, right? If we're going to like move forward with this LSA method, you know, if I slap a magnetic field on this, does it inhibit the turbulence? Does it help? Does the magnetic energy take away from turbulence? These kinds of things. So we ultimately just want to understand the energy profile that like drive explosions and like why things explode. So that's kind of the whole, spiel here. Thanks for listening. I appreciate you guys inviting me to come have a talk. And if you have any more questions, just let me know. Yeah.
Great presentation. You got me a little baffled with the 23 solar mass model.
Okay, yeah.
And how it reaches that stability.
It doesn't look like it's only over 9 or 10 milliseconds, but that is a lot more stability than seen in any of the other models. I know you said you don't know exactly much about
So
it.
you mean like this piece right here?
Yeah.
Yeah, so that's actually the SASE coming in. So the SASE
Right.
provides stability as well. So the SASE adds this sort of like centrifugal acceleration that right keeps things sort of like semi-stable before it like totally collapses to a black hole. And it still has accretion as well, right? So there's still an accretion rate.
But you said that other models have had this too with the 23 solar mass.
Yeah, so generally in like one dimension, people like will model this because once again, these are 1D models that we're extrapolating to 3D that we're starting with. So people have to model this in 1D, and yeah, it's hard to blow it up.
So
And they don't see SASEs though, right?
my final question is,
Yeah.
how much do you have to deviate from that 23 solar masses to reach instability?
How much you need to reach? Oh, to actually like have a collapse or have
Yeah.
a. So first off, if I were to run this longer, it may collapse. But there's actually a really a paper from somebody in my group previously who's now since graduated. Some Dutta Ghosh. She does some good stuff with this. She has a whole study on like all these models where she like dumps in a bunch of mass at like ratio at like a I don't know some kind of grid of like 0.1 solar masses and like tracks just straight up like which ones blow up and which ones don't. And I don't know the answer to that off the top of my head, but I want to say it's like not that far off. I feel like 24 solar masses. If you give me like 2 seconds, if we have the time, I think I have it pulled up because I'm currently writing my thesis, so I have every paper pulled up in the history of time. Actually, I have her thesis pulled up. You know, everyone just want to read my old lab mate's thesis real quick. There's a really nice figure in there that I want to steal right now. Let's see if I can do it quickly. Looks like now. Not in a reasonable amount of time. Okay, yeah, but some Dutta Ghosh, great paper. She does a lot of stuff with like push and things like that. And if you want, you know, when I'm not on the under the gun, I could probably grab you that paper and send it to you. I'll show it to you after this. Yeah.
That's a really good question.
Yeah.
You've got something exploding at 27.
Yeah.
Exploding at 20, and in between it's not.
Yeah. Well, if you want to hear a crazier thing too, right? I mean, so we've run some models. I'll give you a teaser to something I'm also confused about that I still haven't solved, which is we've run some models with magnetic fields, and we ran one model. Do I have it on here?
It's a zero metalist. I mean, it's a zero magnetic field.
Yeah, these are at zero.
So it's sort of the magnetic field here is irrelevant because you've made it so.
Yes.
So what's happening at 23?
Right. So I guess to that point is with the magnetic field, when I apply this, I have a run where I do a 10 to the 10 magnetic field, I have a 10 to the 12, and I have a 0 magnetic field, and I compare these things. 10 to the 0 or 0 magnetic field at 10 to the 12 behave very similarly. 10 to the 10, wildly different. Like it's like it actually explodes like really fast for some reason, and it's like right in the middle, right? That doesn't seem to answer any trends. So I don't know the answer to that one either, but same with this one. Like it's sort of baffling, and supernova physics is kind of complicated, so I don't have a strong answer. I mean, if my first gut is the compactness is high of the progenitor model. Why would the compactness be high? Probably differences in abundances, right? Probably more dense material at the core. Something you choose? No, something you measure. So it's generally just, it's like you pick a mass, let's say compactness 2.0. So you find where there's 2.0 solar masses, and then you read off the radius, and then it's just the ratio of 2.0 divided by whatever radius that is. Just some kind of like quantity that people use to track these things.
So the density profile, so the progenitor mass.
Yes, yeah, density profile depends on the progenitor mass, which totally depends on the stellar evolution model you've used to evolve it to that point, which is also highly dependent and highly sort of like built on its own field, right? Because there's also these are Kepler progenitor models, which is one particular thing, but there's also MESA, which is a very like popular open source stellar evolution code now. Yeah.
I have a very nice suggestion, and before that, I want to clarify, this is hydro, 3D,
Yes.
bronze, right, no magnetic field.
Oh, yeah, well, magnetic fields off. Yeah. Yes.
So I think in whatever way we calculate the turbulent energy, it should be associated with some other driving mechanism. For example, here it's probably all the energy is coming from gravity.
Yeah.
The matter is falling, but it has to be connected with thermal energy.
Yeah.
You try to correlate the turbulent energy with the thermal energy, so that if there is a correlation or anti-correlation in time series.
Yeah, I think that's fair, right? It does need a source term for this turbulent energy, right? If we keep considering this a separate energy source, but really turbulent energy is just a subset of the kinetic energy. So it's probably just a product of gravitational energy ultimately, right? And internal energy, right? Which internal energy is our catch-all term for just general heating and like nuclear stuff, right? So we don't have like it doesn't have its own transport equation. It's just tied into the transport equation from kinetic energy. And then we're trying to just extract out what is the turbulent piece of the kinetic energy.
Very interesting talk.
Thank you.
I have a more like a technical question.
Sure.
So if you increase the resolution
Yes.
if the star tends to explode more.
So that's a great question. I've only run this at one fixed resolution. That's actually a whole axis of study with this and would be really interesting to do. The problem is we're probably at the lowest resolution that we can like reasonably run the simulation. This took me like 2 months per simulation to run. So like we probably need to like go on the other end of things of like increasing the grid size to see what happens. We ran one with like an increased grid size, but not enough to make any claims about if it explodes sooner or later, right? I think I didn't have a direct comparison with it either. But there's space for that to use this code for that, absolutely. And also for clarity, this code doesn't simulate the entire star in 3D. This simulates only the core that we care about, and the rest is done in a 1D approximation. And it uses the 1D data for boundary conditions. Yeah.
So the sort of takeaway is, maybe turbulence isn't as big of a contributor. Curious if you think the SSA model is tracking something different that might instead be physically motivated.
Yeah, I think the SSA model is tracking convection, right? I think it's really capturing convection. And if we kind of think about like where it's pulling its velocity data from, right? If I'm at a point here that's isolated from something over here, and I'm doing a spherical average like this, then presumably I'm capturing that the average radial velocity across this whole shell should be inward, right? I mean, on the whole, in a supernova that's collapsing, everything should be radially inward for the most part. Even if they're convective cells, if you take a big average, you're probably just going to get radial inward, right? So theoretically, your deviations from radial inward, your big radial inward velocity is going to be maybe a large radial outward velocity, right? And so that's going to be your largest deviation. And so that's kind of my like argument for why this SSA method is probably tracking convection more than anything else, which is very well present, right? And it's a huge part of the SAR, right? But we care about the small IDs rather than the like big, like overarching welling up from the base. I mean, we care about that too in other contexts, but in my context, I care about one really specific thing. Yeah.
You have really focused on it, but it does seem rather that what you're doing could tell us what the boundary between neutron star and black hole is.
Yeah.
It's going to be a black hole if enough stuff is left behind to make it a black hole.
Yeah.
No. So can you make any comment about where that boundary is and whether that might be compared with observations, or what's the status?
Yeah, so that's actually the biggest part of this is like, we know that there's twofold to this, right? So there's one, if it explodes, we leave a remnant protoneutron star generally, right? That being said, this protoneutron star could be, in excess of whatever mass it needs to be to, like, it could be, like its remnant mass could be in excess of whatever it needs to be collapse into a black hole, and maybe it could later like sort of, collapse in, right? I don't know if you've seen these things with like neutron star mergers where you can get like hypermassive neutron stars briefly, but like it could in theory be like a hypermassive neutron star. Realistically, probably not. So anyway, to get back to your question though, the status is unclear, but we want to understand how these explosion profiles do tell us. And that's ultimately what we want to predict. That's a big question of the field. And because I was able to like focus in on a couple 3D simulations, I can make some predictions about in these conditions, they'll probably explode. But the only big like parameter studies are in one dimension because that's all we can like really afford. Excuse me. So like, I don't have a confident answer on that, but in the same paper by some data Ghosh that I kind of mentioned, that same figure also shows a ton of ones that collapse into black holes based on choice of solar mass initial, but also many other parameters, because just like with any theoretical model, there's like a ton of knobs you can tweak, right? This equation of state thing I kind of mentioned has like 10 million knobs. Your progenitor has 10 million knobs that you can turn, right? So ultimately making like a strong prediction about what stars will go supernova and what stars will come in black hole is not clear. To me, at least, yeah. But
somewhere around 20.
Well, maybe because 40 blows up, right? So we also have S27 blows up, 40 blows up, but then sometimes random ones don't blow up. I really should find this figure because actually it's in my thesis. Let me just pull my thesis up. Nobody judge my thesis. This is not my committee talk. Yeah. Here we go. All right. Yeah.
It's a mess.
Yeah.
Yeah, it is a mess. It's kind of the short answer to the field. Yes, and also here, let me pull this up. I have the figure. Is this the figure you just showed?
No, actually, that's.
Yeah, so this is a similar one, but yeah, different These are four metallicity studies. This is your Zams mass of your models blowing up. Black means it turned into a black hole. Colored means it blew up. And who knows, right? I mean, and then, you know, just kind of all kinds of different parameters. And so these blow up, these don't, these are in the middle, we got some over here. So like the heaviest ones tend not to, but then if you change the metallicity, then they do, then they don't at all. So. Yeah, go ahead.
So it's maybe technical question, but if you, so my question is about reproducibility.
Yeah.
So if you run the simulation where the star doesn't explode.
Yeah, if I ran
If
S23.
you run this simulation again.
Yeah.
It's gonna not explode.
Presumably, yes, it should not explode. And further, it should be pretty close to what happens here, right? They should be very deterministic for the most part, outside of numerical noise, right? Which small instabilities result in large deviations, right? Because these are very like chaotic systems. So they're very sort of like, well, maybe chaotic is a bit too extreme of a term for it. It has specific meaning, but it's very unstable systems, right? So minor deviations can result in like large changes. But for the most part, they will not explode, right? That's not going to change.
So do you see any issue random perturbation or any more?
I mean, the seeding comes from just like general numerical noise in terms of like doing these like calculations, but no need to seed otherwise. So the code just takes care of it.
Because my experience is asking that unless the perturbative property doesn't excite, if your resolution is pretty good.
Oh, yeah. Well, this does, I mean, this does, so this does develop staticity, and you can't quite see it here, but if you looked at the maximum radius, you see this like oscillation show up. But I haven't done an in-depth study of the SASE. I've just like made little movies where I kind of like watch it over time. And I could see what looks like a SASE form, but I haven't done like, I haven't actually done the decomposition, get like modes of like what in the SASE have shown up. Yeah, supernova crazy. All right, cool, thank you. And if you have any more questions, come bother me. I'll be around the rest of the day. So my office is
D211.
somewhere else. Yeah, D211. Kind of lost in this building.